All right. Thanks a lot. So yeah, welcome to week 4. Today, again, there are going to be maybe three videos today. So the first video is about more technical. It's like a literature review. I mean, more like a, I don't know, timeline review over the last 20 years or so about how we got to where we are today, right? Like, so last week, we talked about in one of the videos. Um, about some of these recent advances in reinforcement learning and so on. But I wanted to provide some sort of more context into the shape at which the trajectory has gone and what the technical developments of these. Again, this is maybe a bit more on the technical side, and we don't need to know everything. Like in the end, like for using ChatGPT, we don't need to know all the transformer works and all of that stuff. But I think it's important to like reflect on the and have a documentation of how the field has evolved very quickly, right? Like over the what I'll show you is over the course of like 10 years or so, like things have changed so much so quickly, and I think it's really important to kind of document that, like learn about the history, learn about like how these things came about, and like what it means to where we are currently, which is the agents, right? Like the today, I think the coming age of AI is going to be agents. So it's no longer going to be this sort of window of ChatGPT where you type in something. I'll show you some examples in another video where I'll show you how AI agents work, how I use them, and you can also use and this is one of your assignments this week is to work on an AI agent yourself, give it a problem, document your experience, what worked, what did not work, why you think it worked, why it did not, may not have worked, and things like that. Okay, so let's get started. So today we're going to again like have these three pillars. The first is what we call the scaling loss last week. How scale is something that keeps winning all the time. So this is all. I mean, we keep coming back to this Sutton's bitter lesson thing, like where throw a scale at it and suddenly you learn a lot, right? Like so same method, same general method, you give more compute and more data, it gets you like more intelligence, more knowledge. And then the second is this idea of how transformers as an architecture came out to be, and how they just started dominating everything from text, vision, image, audio, video, and a bunch of others, like now time series, protein folding, and a bunch of things like that. And the third thing is also related to what we talked about last week, which is reinforcement learning. But again, I want to establish this sort of trajectory of reinforcement learning, which is how reinforcement learning started in the 90s. Nobody cared back then. Nobody could operationalize it at that, that well. And Sutton, for instance, Richard Sutton is one of the pioneers of reinforcement learning. But today, it keeps coming back, and we, spent a long time last week talking about reinforcement learning with verifiable rewards. So we'll come back to that and like put all of these together. Um, so yeah, so we'll go through each of them and then revisit each through line as we cross it. And then all of these will come together to form the AI agents that we know of today. And then we'll put our hands on and play with some of the agents. Okay, so looking at this, the trajectory, like so, this I think in the files part in the materials, like I uploaded this PDF that contains all the papers that I referred to today. It's around 35 papers. So obviously, I'm not expecting you to read all the 35 papers. It's good to know these papers, know about them, know the authors, because you keep seeing the same people again and again, and you keep seeing the sort of evolution of like how things changed and all of that stuff. Uh, so yeah, this is like again, like I said, like this is more like calibration through history, right? Like so, what we learned during week 1 is also something around that, right? Like when you place a result on this timeline, you can judge whether a new claim is genuine or it's very predictable, right? Like so, that's the idea. So for each paper, we aim to just recognize its name, place it on a timeline, and then maybe one sentence or so around why it mattered. And then again, these papers are extremely influential. I mean, they've influenced thousands of papers and maybe hundreds of millions of people's lives, like meaning, people are using these kind of technologies built on top of these papers. So they're very, very, very important. And so we'll follow it in four stages. So one is the sort of hardware, then the vision era, which is the starting of the deep learning revolution that started off the AI revolution, that recent AI revolution. Then we look at this thing called sequence modeling, went on for a few years, and then finally transformers that are now like the dominant methodology, the dominant modality, the technology. Okay, this is over this sort of 20-year period. So we start with 2004, where these things called GPUs, graphics processing units, where I mean, the one of the biggest breakthroughs for this entire field has been the discovery that these graphics processing units, which are usually used to render computer games and like animations and like things like that faster, where someone really realized that these can be used to also speed up matrix multiplications and then other forms of operations that are required for linear algebra. So that was a big breakthrough actually, like that led to NVIDIA is now like a $1 trillion company, and like this technology being like really, really good and fast and scales and all of that stuff. So, okay, so we'll go through this 2004, the GPU, uh, uh, how GPUs became more general purpose. It went from gaming to something that people use for AI. Then 2012 is AlexNet. Anyway, we'll go through them, right? So there's this sort of paradigm shift. Like people start doing things very differently every few years. And after 2014, it's every year, maybe so 2004, 2012, there's a large gap. 2012 to 2017 is a large gap. Then, it's 18, 20, 22, 24, so it's a very quick succession. Um, Okay, so the phase one in this is this sort of hardware phase. So we have four phases, like I said. A hardware phase, which is, again, this is one of the main breakthroughs that enabled a lot of this happening over the last 20 years or so, which is that, people took these graphics processing unit, which is the main person here is this Buck, Ian Buck. Like he went on to later, work at NVIDIA, like led this sort of development of this CUDA programming language at NVIDIA, which also is where like the language in which people program. It's a low-level assembly like programming language that interacts with the hardware. It's very efficient, and so basically. Yeah, so the idea here is they realize that these graphics processing units can be general purpose stream compute devices, meaning you send in some raw bits of data like in a stream, and then you can process them and produce an output that is interesting. And So it wrote this sort of programming model that made GPU compute usable beyond just rendering of frames and scenes, things like that. And so we can trace out that lineage of GPUs being used for general purpose computing to then the deep learning revolution, which is AlexNet, which is trained on consumer grade like GPUs. So people, I can talk about that in the next slide. Um, so yeah, this is around like 1,000x speed up over a regular CPU, right? Like so that kind of really accelerates the kinds of things you can do with GPUs. And that's why, we really are bottleneck currently for the AI progress with the availability of GPUs, and the GPUs can do a lot of like really, really efficient and high grade computing. So here, I mean, at least for me, I don't know if you agree. The important takeaway here is this sort of interdisciplinary research. So, people in gaming, these were people working computer vision, graphics processing. They took that, they applied that to show that you could take these streams of data, process it there. Then people from deep learning, computer science, and computer vision. They took it, applied it to their field, and then it went in from there. Okay, in 2012, there's this is the paper that is credited as what is called the deep learning revolution, the beginning of the deep learning revolution. Again, deep learning is this concept of training these very large, deep neural networks. So I think we had some example of neural network last week. It's this sort of neurons that activate, and then you have a forward pass, backward pass, then they store some information that encodes this sort of learning, and that's how your brain also works. But these neural networks are much smaller scale. The idea is that as you go deeper into these networks, so if you have a network that is whatever 50 layers deep, then it encodes a lot more information. And these information here is the same as your parameters. Like if you say 175 billion parameter model, it's encoding this sort of information, compressing information, and storing it in these forms of these weights, right? Like so similar. So it's early on, right? Like, and deep learning has existed since the 90s. I remember when I was in the university in the early 2000s, maybe mid 2000s. So then, we had a chapter on neural networks and nobody cared. Like everyone used to say, oh yeah, this is just a historic relic. Like nobody's using it. Even in like 2007, 8, that time. It was considered like that. Like it's just a mathematical. I mean, the good thing is they had some very good properties and all of that stuff, but nobody really knew how to train them efficiently and all of that stuff. And one of the key big breakthroughs here is this AlexNet paper, which showed that you can train these very deep neural networks using these consumer grade GPUs that made it possible that to have these sort of very deep neural networks. And what they did is they applied that to real world task. This is called the ImageNet recognition task, which is just classification of images. Which is again now it's almost a solved task, but back in the day, like it was really a big deal to get a huge bump in accuracy on this task. And so the people behind this are Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton. Sutskever and Hinton are like super, like these godfather figures. So Hinton for sure, like he's the Turing Award winner. Sutskever is like very, very well known. I think we talked about him last week as well. Like he's the one who was talking about okay, the training data is running out now, this new RIP stock and things like that. If you want, you can go back and refer to that. So this is, there was a huge breakthrough. And then, so again, like the idea here is this concept of that, Richard Sutton kind of formalizes a few years later, which is that, you don't, I mean, one of the reasons why this method beat a lot of the other existing methods is there are no handcrafted features here. It's all learned from data. You just throw in a lot of compute, which is GPUs, two GPUs at that time, like which was unimaginable now, but at that time it was a big deal. Uh, Okay, so that was phase one, the hardware phase, and oh, no, sorry, yeah, we moved to vision phase in with AlexNet. But anyway, there's another paper which is called ResNet, which was again a very, I mean, the idea is very simple, but it's a huge breakthrough because it's used even now, like everywhere. The problem with again, it gets a bit technical. Problem with training these very large deep neural networks, so neural networks that are like whatever 50, 100, 150 layers, is that these gradients they collapse, like meaning anyway, so it's mathematical, but these gradients become zero. So you differentiate and then you differentiate that, and so those become zero very easily. So they just had this sort of residual network, which is let the gradients flow straight through, so you add upon what the gradient from the previous layer and things like that. So it did enable this sort of like, again, it's a very simple trick, but it enabled the training of these extremely deep neural networks that are collapsing, that enable these architectures that can solve real world problems. And yeah, that like really like just that one small thing that, okay, you can take these residual connections and use them in the next layer. They just like solve like vision to a large extent, right? Like, and then people use this in many others, like in translation and dialogue, like speech processing, code generation, and so on. And yeah, ResNet paper is a big breakthrough. Like it's, I think, from people at Microsoft or Facebook or Microsoft, actually Microsoft. Okay, so then the next phase is sequence modeling. This is there's a lot of methods in this. I don't know if you've heard of LSTM, GRU. There's another which is RNN, recurrent neural networks, and so on. And like there's a bunch of here really interesting methods here, like including this sort of word to vec, which is converting words into vectors, and like looking at like meaning in the semantic space and things like that. Sequence to sequence is like there's this encoder which reads an input and then outputs one token at a time, and then it is sort of recurrent, like so takes text, outputs text. Then there is attention, which is instead of taking a sequence, producing an output, like you really recognize like automatically which words are more important. So this is called attention. And this attention was later used in transformers. And then, okay, in 2016, Google did a lot of work in this space back in the day. So this is this Google neural machine translation. Previously, the translation used to be on another kind of technology, but in 2016, they deployed this neural translation to billions of users, and then it was one of the first massive deployment of deep learning. Actually, I mean, the Chinese companies like Baidu like had done these sorts of search re-ranking using neural models like even earlier. But anyway, Google is our like the one that we know of. Um, and again, like attention is one technology that was invented in 2014, but it became like very, very important later in the transformer paper, which is the final phase, which is the transformers phase, where transformers just ate up everything. All of these sequence to sequence modeling methods, they are all now defunct, like because transformers just outperforms all of them, right? Like so, the idea here is, I mean, it's much more like, but one of the key things that made transformers very popular is this sort of parallelism. So instead of doing one token at a time, which is sequential, like so it's very slow, you can do this sort of like parallel processing. So the whole sequence processes in parallel, and then the GPU, because the GPU, it really massively enables GPU utilization very effectively. And so it was done again by people at Google. And this was specifically done for language translation and faster training. So it was pitched for translation, but then the people realized that this is going to be very, very, very effective in like doing everything. Like we'll see examples of that. So it was just about translation, but then everything: text, vision, image generation, protein structure. Everything that we know now is a transformer or a transformer adjacent, or something derived from the transformer. Okay, so then 2017, the transformer paper came out, and then 2018, people started experimenting with it, a bunch of different things, and we'll see a couple of examples here of applying transformers. So the first one is GPT-1 and GPT-1 style of works. So a transformer, again, is very technical, but there's an encoder, decoder, and you train each of them. There's an attention layers, a bunch of things like that. So GPT is like a general purpose generative pre-trained transformer. Uh, so it basically is the one application of a transformer is this sort of generation of text. It predicts the next token. This is what we saw in the beginning of the last lecture. So it goes from left to right, predicts the next token. And this is auto-regressive, like meaning it takes text up to length t, then predicts the t plus one, then text up to t plus one, predicts t plus two, and so on, right? And then this is how we got like GPT-1, GPT-2, GPT-3, Chat GPT, all of these stuff, right? Like this is the next token prediction. There's another way in which GPT, this transformer was used, which is BERT, which is bidirectional. Like, so it's not just going from left to right. So people started doing this sort of encoder only models where you look at the whole sentence all at once, mass some words. So this mass language modeling, like we also talked about this last week. It's used for various tasks, which are things like classification, search, embeddings, and so on. It's one of the very, very popular models, but for doing a lot of these natural language processing techniques. And then this also like enabled this sort of pre-train, then fine-tune. I think we looked at fine-tuning last week. Like, so you have a base model that you can then fine-tune for specific tasks. That again, like, is a breakthrough because of BERT and like these sorts of encoder-only models. And so both of these like really work like really, really well. Again, this is a huge breakthrough transformers because of the enabling these sorts of applications. So this general method transformers, and then you put in more compute plus more data in different ways. So you use the encoder, you use the decoder, you train on one of them, you train on different tasks, you get different types of outputs, and we'll also see you can use this for different modalities to get advances in image processing, video processing, and so on. Uh, so then we discovered this sort of scale. So the GPT-2 was 1.5 billion parameter model. GPT-3 was 175 billion parameter model. Again, this is this sort of scaling law that I was talking about. Like as we, I mean, this cuts off at 2024, which is like already ages ago now. But the number of parameters in the billions is like it's really, really increasing, and that really increases the performance as well. Um, Okay, uh, so scaling laws because of this, like really, again, like there was this sort of rush to just put in more data and more compute and more data, more compute into these sorts of general purpose technologies. And we saw this last time, the scaling laws model, the scaling laws paper, and the chinchilla paper, which made it the compute parameters and data. And then this chinchilla paper I think has some sort of very nice equation, like very nice results that show that most of these existing models are undertrained, and you can get more out of each of these simpler models. So just providing high quality data will get you very, very far. And then what happened is after a certain time, like people just ran out of data to throw at these models. So the labs became more data bottlenecked, and then we came to this sort of scale. Like so, instead of throwing more data, you wanted to throw more scale, and so you created these massive infrastructures. Like again, like this is 2024 paper, so this looks like child's play now. Like 12,000 GPUs for some model like this. Called mega scale. I don't know what that model is, but I mean, like for instance, now I think GPT-5 or GPT 5.5, they are trained on like hundreds of thousands of GPUs and like massive, like, cross data center training and all of that stuff. Even all of these big models, like Grok, for instance, was trained on like 200,000 GPUs and, so on. So yeah, this became like this sort of massive engineering mega project, right? Like, so all these data centers that are being built are all for enabling this sort of very, very massive training with like hundreds of thousands of GPUs in one place and so on. These are what are called hyperscalers. Anyway, we'll come back to this next week. What is the consequence of having these sorts of massive training and scaling up and up and up? Okay. So we went from the transformer to applications of those, right? Like there are many more, like this. Instruct GPT, which is a reinforcement learning with human feedback on top of a GPT model. And that is, you have this supervised fine tune, which shows good demonstrations, then have a human ranked pairs of answers. This we saw last week. And then you have some sort of optimization policy. These are usually smaller models than GPT, but they're much more well preferred by humans because they're trained on this or fine-tuned on this human feedback. So that enabled this sort of chat GPT like models, which just created a consumer AI moment, right? Like, so we all got exposed to consumer AI. I mean, GPT-3 existed for a while, before that, but we got because of this sort of instruct models. Uh, Okay, and then the next breakthrough here is chain of thought. Again, this is something we looked at last week, where let's look at the details of what chain of thought, how it came along. So there's this paper again by Google, where I mean, and Ilya is in there, and a bunch of like big names are on that paper, where the idea was just asking these models to think step by step, uh, just enabled it to increase its performance on arithmetic, common sense, symbolic reasoning, and so on. Again, like this is it's just a very simple breakthrough, meaning like people just realize that, okay, if you just ask a model, just in the prompt, say, think step by step, right? Then it enables it to perform these sorts of tasks that are tasks much better than what it would do previously, just giving the model the ability to wait and think and take time, provides better responses. So the model, again, like this is something that is already a capability of the model by virtue of its training, that is now just unlocked by a prompt, right? And I don't know if you remember, like at some point there was this sort of prompt engineering as a field or whatever, right? Like that was at this time, and we don't hear prompt engineering as a thing anymore, like because this is now a different paradigm. At that time, this is 2022. People were thinking of like, okay, you can elicit these sorts of different behaviors just by prompting the model differently. And then what happened is uh, uh, this sort of reasoning capacity was latent, and then the prompt unlocked it. And this told the labs that reasoning was trainable, not just elicitable, like meaning like it's already in the training. If you explicitly operationalize it, like then you can have these sorts of models that can reason, and then you can build on top of that to do these RL with verifiable rewards and things like that. This is okay. Now let's, we looked at those four phases. Now let's look at some of these through lines that come out of these. One is this sort of scale, which Sutton and we talked about this work last week. So just general methods that leverage computation are ultimately more effective and by a large margin. And it's almost every leap, it has been something like this, right? Like which is AlexNet, transformers, GPT-3, AlphaGo, Zero, stable diffusion, like things like that. Uh, so then the second through line is it's not just transformers were built for text, but it really builds and conquers these other modalities as well. So VIT's vision transformer. This is again a conceptual leap in treating images as sequence of patches. So you tokenize those patches, and the same architecture of a transformer, it works. You represent an image as a sequence of these tokens, which are patches from the image, and then it beat like a lot of these convolution neural networks and so on, at especially when you can scale this up. Then there's this CLIP paper, which is again another big breakthrough in 2021 from OpenAI. The idea here is you can do the sort of joint embeddings of content to the same space. So if you remember Word2Vec, that was converting text into mathematical representation. So CLIP represents text and images in the same space. And then there's this diffusion transformer, which is used as a it's used for a lot of these modern image and video generators um, so basically the idea is you have this one transformer architecture or a version of that, and then you can uh, create or build applications of these for different modalities. Let's specifically look at like image generation. So it started with, again, if you look at like 10 years ago, there was this thing called generative adversarial networks, where you have these generator discriminator networks, and then that enables this sort of creation of images. They're called GANs that enabled generating of faces and so on, which was a big breakthrough back then. Then this diffusion as a model came in. Diffusion is just you start with random noise and then you have a neural network that learns to denoise to generate some shapes and things like that. So at first this was overshadowed by GANs, but then it later overtook it. Then this DDPM paper made this sort of diffusion much more competitive in 2020, and then 2021 there was this paper called stable diffusion. I don't know, again, like this was a big breakthrough at that time. That also had a company called Stable Diffusion, which is an open source model and so on, like that combined this sort of latent diffusion with clip text conditioning that enabled this sort of prompting of images. So this sort of text to image as a thing became very, very popular because of this sort of stable diffusion, where the model could understand what, if you say generate a chair that is shaped like an avocado or something. So it knows that even though it might not have seen this, it knows what a chair is, what an avocado is. And so it can put these concepts together and produce a visual output. Again, like this is unbelievably complex, and like we take it for granted now that AI can generate almost anything we ask it to, but that's the idea here is to really appreciate these. Like this did not happen just, I mean, it's not magic, and it's not wasn't an easy pathway. Like there's a huge field that went into here, that a huge background here, like these sorts of incremental breakthroughs that then compounded and like get to what we have now. Um, so anyway, so here there's a bunch of findings. So one is this sort of like in just 8 years. So the start of when 2020 2014, like people said I can generate like extremely high quality HD images of people's faces and realistically looking image and art that is really, really good. Like people would not have believed you. But in just 8 years, we went from the sort of like things that are just a lab curiosity to something that you and I can just now do in a commodity. Like you just go and type it something, you get an image back. Right? Like take it for granted now. The other is this sort of diffusion or like some of these methods, which I mean, it's the same story, right? Like artificial neural networks, deep learning, all of these are like, have been discarded and said, oh yeah, these don't work. They come back and like have these new applications. So it's always, this sort of marriage of, okay, you find this, you have this new breakthrough, and then someone comes up and says, oh yeah, there's this old thing from 10 years ago. I take that, combine it with this breakthrough, and you get a new breakthrough kind of thing. Okay. Okay. So now let's look at just this sort of summary of like how transformers eat every modality. So in 2017, this architecture of transformers was mainly proposed translation. Then 2018 to 20, you have these, like I said, like text understanding, so natural language processing. So using these sort of mass language models, bidirectional encoders, and so on, BERT, and similar models, and then text generation, which is GPT 1, 2, 3. 2020 to 2022, there's more improvements on multimodal capabilities, which is vision language, and then image generation, which is diffusion transformers. 2023 to 2025, like there's more developments beyond just text and images. So audio is now again like you can generate like really good quality audio, video, robotics is the next big frontier that will be solved pretty soon. Like I mean, or at least there'll be a big breakthrough happening. Protein structure, weather, time series, all of these are now transformer based models. Uh, so the specialized architecture that is that experts build is now just this sort of generalized thing. You have a transformer, you throw in a lot of data into that. You just encode, like if it's a vision, you encode it into these patches. If it's a video, you encode it into these frames, and some way of transforming them into this architecture, changing it a bit for that modality, and all of these are now work with a similar kind of architecture or technology behind it, which is the transformers architecture. So this general method keeps beating the specialist designs. even ones built by experts. So there's another the third through line with the stuff that we have learned is the comeback of RL, reinforcement learning. Uh, so AlphaGo Zero is just this sort of like early demonstration of this reinforcement learning with verifiable rewards. So there's people at DeepMind, which was a London-based startup at that time, where basically they just learned how to play a game. Like, it started with the sort of Atari 8-bit games like, I don't know, Pong and things like that. So the computer started learning how to play these games just by looking at previous versions of the game and then learning, what to do to be able to succeed. It's again like it's just like magic if you understand what exactly happened. Like basically, what they did, especially in these playing these games, is it provided a screenshot of the frame of that what is happening, and then the reinforcement learning model really learned that, okay, if you take these sorts of actions, you're going to go towards a path of success. And so it really learned the rules of the game just by looking at some of these frames frame by frame. And this is one of the first proof that reinforcement learning on a verifiable reward, like did you win the game or not, can really reach superhuman performance. And this really sat outside of language for a long, long time. Then it came back twice. Like we have two cases of like reinforcement learning that enable breakthroughs in language. So yeah, this is some examples of this AlphaGo Zero. Again, if you want to go and read about it at that time, like super big breakthrough. The first application of reinforcement learning for language is RLHF, which is 2017 to 2022. Again, like a bunch of papers in this space. 2017, Cristiano, Leike, and so on. Leike is now like a big name, and Anthropic works a lot on safety. And they really showed this sort of learn and reward function. And then Instruct GPT ports it to language. Instruct GPT is the paper that enabled taking a GPT model, creating an instruct fine-tuned version of it that is a response to instructions instead of just as a sentence completion. And here the signal is human preference rather than game outcome. And the reward is fuzzy, right? Like, so human, I mean, you cannot have infinite number of human judgments, so then the model has to make some of these judgments, and this is where you really have these issues of psychophancy and so on. Like, we'll get back to some of these in week 8. Then now we have this reinforcement learning with verifiable rewards. This is the second breakthrough. So RLHF and RLVR, like which enables these sorts of models like O1, OpenAI, O1, O3, DeepSeek, R1, and so on. Uh, and this is again like a huge breakthrough, like which enables this big improvement in benchmarks. So previously these sorts of benchmarks for math and grad level science and so on were like very hard problems for these models. But then once you have these thinking models and these models where you can have again, like all of these are domains where you can have a verifiable reward, like you can have a success or not, right? Math, proofs, science, grades. You can grade these assignments, and coding, is the code successful or not. And then, okay, so this is the history of reinforcement learning. And again, started in the 90s. Then in 2000, in the 2010s, there was this Atari games, AlphaGo Zero, and so on. Worked on these verifiable games. Then 2022, RLHF for language, and then 2024 until now is this RL on verifiable rewards. And this is like we saw last week. This is one of the key breakthroughs that enables the current generation of chatbots that we use. Uh, so each comeback is much broader and much more powerful, capable than the last, right? So okay, now we come to this agentic time, right? Like, so this is how did we get to agents? So the title of the talk. So finally, we get to agents. So basically, what happens is you take this sort of thinking, action, and observation, you put that in a loop, and this is how you get agents, right? Like, so the loop is the model produces a thought, like which is reasoning, takes action, like things like search or run a piece of code, read a file, gets an observation that is the result of that, and then goes back into thinking and so on. Like, and we see this, like, when we run some of these agents, which you will also do as part of your assignment, this is happening constantly. So it's doing some thinking, takes some action, and then gets the observation. And this sort of closing of the loop is a hugely powerful concept. And this was proposed in this ReAct paper in 2022. It's from folks at Princeton and Google. Uh, and the paradigm here is different, that because plain language model, just like the ChatGPT interface that we are all used to, just generates text and stops, right? And ReAct, what it does is, or the sort of agent, is it takes that text and then does some operation on top of it, right? Like, and it looks at what the outcome is and then goes back and does a loop over it. And so here the model can gather information it did not have, recover from a wrong step, and ground each decision in real results rather than what it had done prior. And especially this makes it more, well suited for coding agents, where okay, you write a piece of code, run it, okay, observe the outcome, is this correct or not, did it run or not, and then you learn from it, you go back and do the next step. And this is every coding and browsing agent that you've had since 2024 is a variation based on this React paper. So in 2026, which is where we are currently, most of these models are just a reasoning model plus some tools plus some multi-turn trajectory plus verification of intermediate steps. Basically, again, a reasoning model, which is thinking, taking action, which is these tools, and then some sort of verification of intermediate steps. So the tools means, a file system, a shell, a browser, code execution, memory, things like that. So all these tools that you hear of for AI agents, sure, like Cloud Code or OpenAI Codex and Google Anti-Gravity, Gemini CLI, Cursor, Devin, browser agents, uh, Perplexity has a bunch of agents, things like that. So agents it's not a separate direction of research. It's just combining all of these things together, reasoning, tools, and then verification. Uh, so this is where like we have this sort of current breakthrough. Uh, and so three things have converged over the last 12 months or so to have the current breakthroughs of AI models. One is this reasoning models to plan multi-step trajectories without collapsing after one wrong move. Standardized tool use. There's these concepts called MCPs, which enable the models to use various types of tools. This is MCP is nothing but just a formalized way of telling the model, to use a certain type of tool, and verifiable reward RL. So it's a signal whether the whole trajectory, like, so basically you take a bunch of steps, did this succeed or not? If not, like go back and retrace it and like, do a bunch of other things. And all of these combined together will produce these agents that currently work. And these are all breakthroughs that happened over just the last 1 year or so. Okay, so obviously, I am a very active user of some of these agents, and uh, I've seen their power, like what they can do, what they cannot do. So I'm really, pushing or like talking a lot about AI agents and them being the future and all of that stuff. So we also need to be very clear, as is the concept of discourse for everything that we think about. Okay, that we are strongly supporting, like what is the other side of that, right? Like, so if we are like, okay, AI data centers are bad, okay, why do we think that? What could be the other side of that, right? Like, so that's something that we need to think about and develop as part of this course. So it's the same thing here. Okay, we think AI agents can solve a lot of very good practical problems. I will show you some examples of. But what can they not do, right? Like, that's also something that we need to think about. So the strengths are, tasked with automated verification, code, structured forms, data pipelines, things like that, they can really do very well. In terms of decently working, like, refactoring piece of code, drafting with the human in the loop, where you tell it, okay, this is right, this is wrong. Research with citation checking, like this is a grounding in some sort of knowledge base. Uh, Long horizon open web tasks, this is not a solved problem yet. Like, so if you say, hey, go and book a ticket for the World Cup in 2 months from now, like, it's not able to do that. Like, it's a very too much of a general purpose general thing that it is not able to solve right now. And this is one of the reasons why robots are not a thing, right? Like, so you just leave a robot in your house, it's not able to perform. And then anything that is about facts or recent events or needs some sort of context is a big problem. And we saw last week, like, hallucination as a thing of, like, facts being wrong is no longer the problem, but there's a different type of hallucination where, especially over these sorts of very long trajectories, the model gets and does a lot of things very wrongly. Okay, so today we are launching this. I mean, last week also we observed this, or we mentioned this. Pick an agent of your choice. Again, like, I really, really, really encourage you to do this, because if you don't try it out, like, you really don't realize the power of these AI agents and the progress that the agents have made. So I'll show you a couple of examples today, but I think it's very important for you to also try these out. So I think you can try Google Anti-Gravity. So Google has a free tier for, I mean, they have a free tier, but they also have a pro account for students. So you should use your .edu account to get that pro access until September. Like, they have I don't know how long they will be running that, but you should get access to that. Get Google Anti-Gravity, which is like their agentic interface. So it's basically you can generate, I'll show you some examples of interfaces for Codex and Cloud Code. And then uh, yeah, you pick a task for you that you are interested in. And so the idea is not just to show you a tool. It's general purpose, so you can do whatever you want, like a data analysis, a coding project, creating a website, a research synthesis, personal tasks, like, whatever, things like that. Like, so you can try it out. And the objective is not that, yeah, coding agents are like whatever, these AI agents are amazing. Obviously they are, like, for certain tasks. So our idea is to be able to understand, like, how they work, put all of these things that we mentioned in context, right? Like these three-step pathways of thinking, using tools, observing the output, and then going back to thinking, and so on. So let's, I think we should all go through them. And the idea here is, you know, you need to really clearly define, like, I mean, do your homework on what these AI agents can and cannot do. Like, so you can have, like, a look at, like, what other people are doing on YouTube, for instance, and then decide on your task, work on it. Like, it cannot be too simple, it cannot be too hard. Like, obviously, if you ask it, like I said, like, if you say, hey, book my tickets to whatever, Italy in July, and, like, get me a visa, or something like that. Like, it's not able to do those sorts of open-ended tasks. But if it's a more of a closed task, like data analysis, writing some code, writing some whatever, generating some report, sort of specific style, or things like that, like, you can still do. Um, so yeah, draft and, like, create like a clear analysis plan, and then work on it. Okay, so to summarize today, we talked about this sort of scale, the scaling loss, and all of that stuff. We showed you examples of that scale, right? Like, from AlexNet, then transformers, GPT-3, AlphaZero, diffusion, and so on. Transformers being the dominant modality that we are currently working on, like, that really works. This is the architecture that is enabling a lot of AI progress these days. and then reinforcement learning keeps coming back, and it's coming back better each time. So the latest version, RL on verifiable rewards, is what powers most reasoning models. And then agents are just it's just a bootstrapped version of progress from like multiple different directions into something that is useful. It's not a new breakthrough. It's just a combination of the right tools at the right time to provide something that is useful. Uh, and that's this thing of AI agents. So yeah, I mean, let's start working on the assignment. Again, the assignment is open-ended for a specific reason. It's not a single thing like that. You say, okay, I tried it with this one thing and it failed, and okay, that's the end of the task. That's not what I'm expecting. I want you to really experience the power of these AI agents, where they work, where they don't work, try it out, like and like come up with something that is solid, like methodologically, where you've tried a bunch of things and you feel like it works wonders in a certain thing or does not do a good job. Like how does it compare to your regular whatever ChatGPT, Gemini usage, like on the chat interface, things like that. Like, so yeah, take some time, think about it, like work on it. um, yeah, so then, now I'll just show you, I'll stop the video here and then I'll record another video where I'll show you a bunch of examples of how I use uh, some of these models, these AI agents for my daily tasks. And yeah, I'll see you next week.